السلام عليكم ورحمة الله وبركاته. يسعد صباحكم. اليوم إن شاء الله مكملين بحل الأسئلة. وصلنا ل example 5. Okay, so here in this example we have carbon monoxide gas CO contained within a piston cylinder that simply undergoes three processes in series. So here in this example we have three processes. Okay. Maybe we'll have cycle. Let us see one by one. So process 1 to 2. This process we have constant pressure. So B1 equal B2. Okay. Expansion and it is expansion. So expansion mean we have volume very small compared to volume 1, smaller than B2. So B1 equal B2, which is equal to 5 bar. Okay, this expansion happens from V1 to V2. Okay, so even V1 given, okay, and V2 given, and this is expansion process. Okay, but what is the type of this process? Constant pressure. Okay, so process 2 to 3, constant volume process, and it is cooling from state 2 to state 3 because it's 2 to 3. Okay, where pressure 3 equal to 1 bar. So here in this scenario we already have V2, okay, from previous process, and here it's mentioned constant volume. That means V3 equal V2 equal 1 meter cube because V2 given in previous process. Okay, now again B2 given in a previous process 5 bar. Okay, and B3 equal to 1 bar. Okay, process 3 to 1. So what is the type of this process? Constant volume process. Process 3 to 1 compression from state 3 to the initial state, during which the pressure volume relation. So this is the relation for process 3. What we call this relation? So process 3 to 1, what we can call it? Isothermal process. Okay, why isothermal? Because N equal to 1. Here B multiplied by V, V raised to the power 1. Okay. Okay. Now, part A, sketch the process and series. So here you can notice we start from 1 and we end up with 1. So this is what we can call it cycle. Okay. Now we need to sketch the process in series on BV coordinates. Okay. BV diagram. B, evaluate the work for each process. Okay, we need to find work for each process. Of course, once we need work, we must know what is the type of process. Here we have constant pressure process. Here we have constant volume. Here we have isothermal process. Okay, so no need to derive the equation. No need to start from the integration. So we can write directly the result of the equation. Okay. And at the end find the network in kilojoule. Okay, now let's move to solving board. And first of all, let me summarize the states. Okay, so let me first draw before start solving part A, part B, part C. Let me start with drawing the table. So this is state number. Okay, and here we have pressure, and here we have volume, pressure in bar, okay, and volume in meter cube. Okay, and we have state 1, state 2, state 3. And we'll see if there is any missing information. So state 1, pressure 1, 5 bar. Okay, and from process 1 to 2 we have constant pressure, so this is again 5 bar. Okay, now from process 1 to 2 we have V1, which is 0.2. Okay, and V2 equal to 1 meter cube, and in process 2 to 3 it's mentioned that we have constant volume, then V2 equal V3 بالتالي هذه تساوي 1. And in process 2 to 3 it's mentioned that pressure 3 equal to 1 bar. Okay, so everything is known. None of the states are unknown. Okay, so part A, sketch the process on a PV diagram. So here is the PV, and here V. Now, process 1 to 2, it's mentioned that it is at constant pressure. So constant pressure means, so take a look here, pressure 1 and pressure 2 higher than pressure 3. So I'll start from here. So this is 5. Okay, and it's mentioned in the statement of the problem constant pressure expansion. So expansion means this is V1 and here is, I will name this V2. Okay, so this is happen at a constant pressure. So we'll start from V1, which is equal to 0.2, and we'll end up with V1, V2, which is equal to 1. This is happen at a constant pressure. So this is state 1, and here is state 2, and this is the arrow. Okay, like this, I solve it in detail. Okay, now process 2 to 3, this is happen at a constant volume. Okay, constant volume means V2 equal V3. Okay, and B3 equal to 1. Okay, so we'll go down until we reach state 3. Okay, now process 3 to 1, compression from state 3 to the initial state. Compression at isothermal process, BV equal constant, so the profile will look like this. Okay, so this is isothermal process. Okay, and it is compression. Why compression? Because we go from V3, this is equal V3, because we are going from V3 to V1. Okay, like this, we draw the BV diagram. This is part A. Okay, now part B, we need to find out work for each process. So process 1 to 2, in the statement of the problem it's mentioned that this is constant pressure, so here B constant. So work 1 to 2 equal to, B will go outside the integration, and we end up with V final minus V initial. Okay, and this is equal to pressure 1 or pressure 2 equal 5 bar. Okay, so this is 5 bar, and we need to convert it because it's mentioned that find work in kilojoule. So this is multiplied by every 1 bar gives us 100 watt, 100 kilopascal. Okay, Okay, and this is multiplied by, so bar with bar cancel out, and this is multiplied by V2, which is 1 minus V1 point 2. Okay, and this is equal. So work 1 to 2 equal to 400 kilojoule. Okay, so this is bar process 1 to 2. Now, the process, process 2 to 3. So in this process, V is constant volume. So work from 2 to 3. So notice that always we write subscript, not delta. Okay. So if volume constant, that means work equal to 0. Okay. Remember. طيب. Let's see the final process. So now process 3 to 1. What do we have? BV equal constant. So BV equal constant means work 3 to 1 equal to BV ln V final, which state is final state? Yes, V1 is the final state divided by initial state V3. Okay, so because this is initial start and this is end state. Okay, so and here I can write anything, either 3 3 or 1 1. So I write 1 1. Okay, so be careful. Okay, so this is equal B1, which is again 5 bar converted to kilo Pascal. This is 500 kilopascal multiplied by V1, which is 0.2, multiplied by ln 0.2 divided by 1, and this is give us, once we have compression, you must expect to get minus sign. Okay, so minus 160.9 kilojoule. Okay, now this is part B. This is work for each process. Now part C, we need to find, let me change the color. Part C, we need to find W net. W net equal to work 1 2 plus work for process 2 to 3 and plus work 3 to 1, summation of the work for the whole cycle. Work 1 to 2, which is 400 kilojoule plus 0, okay, plus or minus 160.9, and W net from here equal to plus 239.1 kilojoule. And this plus means what? Means work done by the system. So the network is done by the system. Okay, let's go back to the solving, to the PowerPoint. So this is the solution, detailed solution for this example. Let's see another example. And here is the PV diagram. Okay, so it is detailed one. don't forget to draw arrows. Okay, state number. Okay, so everything is important. If you forget any single detail, I will deduct mark from you. Okay. Okay, let's see another example. Okay, here example number 6. Carbon monoxide gas, again, contained within a piston cylinder assembly undergoes three processes in series. So here we have process 1 to 2 again. Okay, and this is expansion from B1 5 bar V1 to V2 1 meter cube, during which pressure volume relationship is PV equal to constant. So this is isothermal scenario. Okay. Now process 2 to 3, constant volume. So V2 equal V3. Heating from state 2 to state 3, where pressure 3 equal to 5 bar. Okay. Process 3 to 1, constant pressure process. So V3 equal V1. Compression to the initial state. Now, the required from this problem, sketch the process on a BV and evaluate work for each process. Okay, let's move to the solving board. Now, here what do we have? We have, let me start with writing or drawing the table, state number. I want to make sure that we have all the states information. So this is bar, and here we have volume in meter cube. This is very important, by the way. 1, 2, 3. Just to make sure that we have everything before start solve. And in order to draw BV, we need to know the exact location of each state. So B1 equal to process 1 to 2 expansion, so volume will increase. Okay, and B1 given to be 5 bar. Okay, but B2 till now is unknown. We'll see if it's mentioned in the other process. V1 and V2 again given, and they are equal to V1.2 and V1 equal 1. This is for process 1 to 2. Now process 2 to 3, constant volume. Constant volume means V2 equal V3. So here again 1. Okay, heating from state 2 to state where the pressure 3 equal to 5 bar. So this one is given. Process 3 to 1, constant pressure. Constant pressure. Okay, so constant pressure for 1 and 3. So yes, they are same. Okay. And it is compression to initial state. So we end up with this one is unknown. Okay. And in order to draw the BV diagram, we need, so let me try draw it for you to see whether we can draw it or not. So this is bar, pressure, and bar. Okay, and this is volume in meter cube. Now, state or process 1 to 2, this is expansion, and V1 is 0.2, and V2 is 1. And we have expansion, okay. Okay. But V2 is unknown, okay. So this is expansion from 1 to 2, but we cannot know where is state 2 located exactly. So let us first go and find out the unknown, okay. Now process 1 to 2, 1 to 2, what do we have? We have the relation. So BV11 equal B2. This is isothermal relation. So from here, B2 equal V1, sorry, this is 2 over V2. Okay, and this is equal V1 5 bar. No need to convert because at the end I'll convert everything. Okay, now V1 equal to 0.2 and V2 equal to 1. So this is equal 1 bar. So as expected, process 1 to 2 expansion. Okay, expansion pressure will decrease. Okay, so here we have 5. This is B1. This is state 1. Okay, and this is expansion until we reach isothermal relation, till we reach pressure 2, which is equal to, so here I can write 1. Okay, so here is the direction of this process. Now, process 2 to 3, constant volume, 1. Okay, and the pressure will increase. So you can take a look here. Pressure increase from 1 to 5. So at a constant volume, will increase from 2 to 3. Okay. Now process 3 to 1 from the statement of the problem. Constant pressure, compression. So compression will go like this at a constant pressure. Okay. So in this scenario, we could draw the PV diagram. Okay. Now, the other requirement, we need to find out work for each process. So, work for each process. Do you know what? Let me erase those. Okay. So, we can see the table while we solve. Okay, then work from 1 to 2. Work from 1 to 2, this is isothermal process, BV equal constant. So this is equal V1 ln V2 final state divided by initial state. Okay, and this is equal to B1 5 bar or 500. We need to convert it always to kilopascal, from bar to kilopascal, multiplied by V1, which is 0.2, multiplied by, this is compression, okay, or expansion. Yeah, this is expansion. So the work here 1 to 2 will be positive. Okay, multiplied by ln V2, which is 1, divided by 0.2. And the answer is 100, positive 160.9 kilopascal or kilojoules. Okay, so this is work 1 to 2. Now, work 2 to 3. Here we have constant volume, then this is 0 directly. Work 3 to 1. Here we have constant pressure, so B constant, either 1 or 3, multiplied by final state minus initial state. Okay. Because this is final, and this is start point, and this is end state. Okay, so subtract final minus initial. So B1 500 kilo Pascal multiplied by V1, which is 0.2. This is compression. Okay, this is constant pressure compression. So compression means we got minus W. Okay, minus V3, which is equal again to 1. Okay, so V3, let me check. Yes, V3 equal to 1, and this is equal to minus 400 kilojoule. Okay, so if I need again W net, I will sum all of them, which is 160.9 plus 0 minus 400, and we'll get minus 239.1 kilojoule. Okay. Okay. So this is example number 6. Okay. Now let's see another example. Example number 7. Again, we have carbon monoxide gas contained within a piston cylinder assembly undergoes a 3 process in series. So process 1 to 2, we have compression. Compression means we'll have minus W, okay, at a constant pressure. So constant pressure means 1 to 2 will equal V final, which is 2, minus V initial. And here we can substitute 1 or 2. Okay, and of course this will give us minus magnitude, okay, because this is negative, because this is compression. And V1 given, state 2 volume for state 2 is not given. Okay, we'll see if it is mentioned somewhere in the remaining process. So process 2 to 3, we have constant volume, so V2 equal V3, heating to state 3, where V3 equal to 50 bar. Okay, so pressure increase due to heating to 50 bar at a constant volume. So V2 unknown and V3 is known. Okay, volume 3 still it's not known. Process 3 to 1 expansion, and this is constant volume, by the way. What we'll have work 2 to 3 equal to 0. Okay, now expansion, and we have isothermal relation. Okay, then work 3 to 1 equal PV ln V1 over V3. So this is expansion to initial state during which pressure volume relationship given in this equation. Sketch the process on a PV coordinates. Evaluate the volume at state 2. So we need to find out volume 2 in meter cube and the work for each process. Okay, same requirements every time. Now, I will leave this problem for you as a bonus. Okay, so I need from you to record a video that will show step-by-step solution for this problem. Example number 7. Okay, so I need step-by-step video due to Thursday. Okay, so اللي بدي إياه منكم تصوروا فيديو طريقة الحل step by step زي ما أنا بحل لكم الأسئلة. اوكي، وهذا بونص تاسك، وبدي الحل يكون جاهز خلال بنهاية نهار يوم الخميس. تمام، so this is bonus task. هي بونص. اوكي، بونص كم مقدار البونص هحدده later on. Okay, let's continue. Chapter 2, continuation of Chapter 2, Energy and First Law of Thermodynamic for closed system. So الأشياء اللي جاية فقط حتكون للclosed system. No mass crossing the boundary. Only energy can cross the boundary. Energy of type work or Q. Okay. First law of thermodynamics for a closed system, or we can use another word which is control mass. Mass is controlled. Okay, nothing lost. Mass remain constant. Okay, so here you can see in this figure that this is a system or a closed system. Okay, where Q energy can cross the boundary, either entering or leaving, and work the same. Can be entered or leaving. Okay, so Q can be gained, system gain heat or lose heat. Okay, gain heat positive, lose heat negative, or work can be done by the system. Okay, positive, or work done on the system, negative. Remember sign convention. So it's defined as a quantity of matter chosen for study. No mass can cross its boundary, but energy can. Here in this slide we'll see a number of experiments. Okay, so experiment 1, when we don't have any work. Okay, nothing cross the boundary in terms of work, but we have Q cross the boundary in terms of Q. Okay, so the total energy stored in the system equal to 5 kilojoule. Okay, 5, or we can say plus 5. Okay, Q is gained, system gain the energy. You can notice that we have here control surface. Okay, so we have a Q crossing the boundary. So the description of this experiment, if we transfer 5 kilojoule of heat to a potato, its total energy will increase. Increased mean plus sign. Okay, أحيانا في نص الأسئلة نيجي بنحكي energy gained or any energy increased. Energy increased means we have positive value. Okay, experiment 2, again we don't have any work. Okay, here we have this geometry and this is the control surface. Okay, here we have energy lost to the surrounding. Okay, and here we have energy gained from the surrounding to the system. Okay, so the amount of energy change of energy or energy stored in the system equal to Q net summation. So here we have 15 plus, okay, minus the amount of energy lost. So the result is positive 12. Okay, so here this is why it is positive. Okay, so heat a water in a pan by transferring 15 kilojoule from the range. Okay, so here we have a pan and at the bottom we have range. Okay, فين غاز. Okay, وفي عندي heat at the bottom. Okay, so في عندي Q transfer inside من الغاز اللي 15. Okay, وفي عندي 3 كيلو lost to the surrounding. That means energy change for the system equal to 12. Now experiment 3, we don't have any Q loss or gained. Okay, that means we have a diabatic system. Diabatic system means we have insulation. You can notice that we have here this color. Okay, here again we have a diabatic. So here in the first example, we have work entering the system in the form of electrical work. Okay, electrical work. What is the amount of electrical work? 5 kilojoules. So the amount of energy change is 5 kilojoule. Here we have mechanical work entering the system. The amount of this mechanical work is 5 kilojoule. So the amount of energy change plus 5 plus 8 kilojoule. Okay, here we have plus 5 kilojoule. Okay, Now someone of you will come and ask me, so if we have work entering the system, work done on the system, means we have minus, okay, and here the same, we have minus. So why it is positive? Why work entering the system positive? Why it's not minus? Because the amount of energy change for the system will gain, okay, will gain work, okay. So heat an insulated room with electrical heater, work will equal 5 kilojoule. So that means energy stored will equal to 5 kilojoule. Replace electric heater with paddle wheel, mechanical work will equal to again 5 kilojoule. Okay, so we'll see why we replace minus with a plus in the coming slide. Okay, so but remember here, this is minus work entering, but we replace it with positive. Okay, we'll see why this happens like this. Experiment 4, again we have a diabatic system. You can notice here that this is insulated. Okay, and here we have the third type of the work, which is boundary work. Work done on the system. This is minus. Okay, tally this will be positive. Energy stored in the system. The system internal with it. So if we do 10 kilojoule of boundary work on the system internal energy, or the system will store an energy which will increase its energy by 10 kilojoule. Okay. Okay. Experiment 5. If we have yes, experiment 5. If we have a Q in, Q out, work in. Okay. So Q out is minus, Q in is positive. W boundary, this is W, this we have here, sorry, we have here work in, okay, this is minus again, and here we have work out, okay, this is work done by the system, this is positive, okay, so the total amount is what? So delta E will equal Q, we have 15 minus 3, okay, which is equal to 12. Or do you know what? Let me write it Q. Okay, this is a Q. Now delta work will equal to minus 6 plus 4, and here we have minus 2 done from the surrounding on the, so we have here minus 2 from the surrounding on the system. So the total amount of work of or energy stored in the system, delta E, will equal to 12 plus 2, and this is equal to 14 amount of energy stored in the system. Okay, so the internal energy stored by the system is 40. Now we need a relation that will assure for us that every time we'll know what to do exactly, without assuming that energy or work entering the system means internal will increase. So this is lead us to this energy. Total energy entering the system minus total energy leaving the system will equal to the change in the total energy of the system. And this minus sign here will assure for us that everything will be according to our sign convention. Okay, I will explain it in more details in the coming slide. So based on the previous experimental observation, the conservation of energy principle, or we call it what? First law first law of thermodynamics. Okay, first law of thermodynamics. So energy in minus energy out equal delta E. On a rate basis, so this one is energy and its unit is joule. On a rate basis, uppercase or capital letters with dot means we have energy joule per second or watt. Okay, so energy in minus energy out equal delta E. Where this is with dot means rate of net energy transfer by heat, work, and mass. Since we are talking about closed system, this is not there. Okay, but this is general equation. This is why we mention here mass. And here rate of change in the total energy of the system. Change in the total energy stored by the system. Now let us discuss the right hand side, this one, okay, of the first law, see, not, we can replace first law of thermodynamics or conservation of energy principle. So delta E, amount of energy stored in the system, either it's in the type or it's not either. This is equal to internal energy stored or change plus the change in the kinetic energy plus the change in the potential energy. Usually, in the thermodynamic problems, usually kinetic energy and potential energy are very small, so we ignore them. So we end up with change of the energy of the system for closed system equal delta U, which is equal, this is joule, so anything uppercase, okay, joule, and this one is again joule, or this is equal specific internal energy multiplied by mass, so this is internal energy. Okay, I think we demonstrated. And this one is same, but we add specific. Okay, and specific, its unit is joule per kilogram. Okay, or you will find it kilojoule or megajoule. Okay, does not matter. And this is mass. Kilogram. Okay. Okay. Now let's turn to the left hand side of the first law equation. So this is the left hand side. Okay, energy in minus energy out. So energy in could be in the form of Q, work in, mass in, energy mass in. And energy out, it could be in the shape of Q, work, or energy from mass out. Since we are talking about closed system, then these two terms go to 0. And remember, the right hand side, we agree that this is equal to delta U. Okay, and notice that all the letters are capital letters. Okay, Q, W, energy, mass. Okay, so this is equal to 0 because we have a closed system. There is no mass in, mass out. Now Qn plus Wn minus from the equation, okay, Q out plus W out equal delta E. If we rearrange both Q together and work together, we'll get Qn minus Q out plus Wn minus W out equal delta E for the system. Or we can, usually we assume this Qn very larger than Q out and Wn very larger or smaller than W out. Then we end up with this equation. Q net N minus W net equal delta E. And this is what happened in this example. Remember this example here. When we said we have W equal to minus 2 and Q equal to 12, then we must write like this. based on the final equation, delta E for the system. So this is a 12, and here minus 2, which give us 14. Okay, so here where it comes. Because delta E, energy for the system, energy change, it will increase up to 14. Why? Because this is minus 2, it is entering to the system. So energy of the system will increase. Okay, so the equation اللي طلعناها هي اللي رايحة تتكفل بتعديل الإشارات والتظبيط. Okay, so usually we drop the subscript here. Okay, usually we drop the subscript, so we end up with this equation. And notice here the letters. If it is uppercase without dot, this is joule. If it is with dot, this is joule per second or watt. If it is lowercase, then this is specific per kilogram. Okay, here is specific energy. Now we'll solve problems, but I will postpone those problems until Thursday lecture. But remember, we have a bonus test. Until then, see you soon, inshallah.